Today we will discuss about AC applications of the operation amplifier. So far we have discussed about DC applications, and then we calculated various errors associated with the DC amplifiers and so on. Now we will discuss about AC applications of the operation amplifier. Now, if we look back what is the operation amplifier and so on, that we had seen that the basic simple operation amplifier was looking like this. We had input stage reference amplifier essentially, and that is given to minus 15 volt, and then we have connected this, and this is acting as a non inverting input, and then the output was here, and then the feedback was given to the minus terminal like this. Now, this is a basic operation amplifier we had discussed initially. So, we will use the same model to see what is the problem in using the op amp for AC applications, because we may think that we can have a operation amplifier, and then for example, if we want to amplify, the simplest thing would be similar to DC. We can have a two gain setting resistors and give a signal here, and then you get the output voltage. Now, the gain actually is given by RF by R1. In this case, it is 1 plus RF by R1, similar to DC, that what we had discussed earlier. In AC applications, of course, there are other advantages, that one need not worry about the DC voltage drift, because if I have a amplifier, then I can always block the DC voltage and take only the AC voltage using a decoupling capacitor. So, we can have a decoupling capacitor and then take the AC output. In that case, the offset voltage, bias current error, all these things goes up, which looks to be much easier, because the lots of problem get solved because of this because of the elimination of this DC problem. But nevertheless, there are issues involved in AC amplifier. That is what is the main worry is that the stability of the amplifier we have to worry, and then the second one is bandwidth. What is the bandwidth? And the third problem is slew rate related issue. So, these issues creates additional problem as far as AC amplifier is concerned. Now, what is the problem due to slew rate, and then what is the problem due to the stability? Let us look at the stability problem. For that, we go back to our operation amplifier circuit. Now, in this case, if I am trying to amplify AC voltage, for example, I apply AC voltage here and trying to get amplified AC output, then we have issues mainly due to there are capacitance between this this called Miller effect capacitance. Actually, this capacitor is coming due to the diffusion charges, because charge that is diffusing it takes its own time. So, that is represented as a equivalent capacitance here. This is the famous Miller effect capacitance, and similarly we have capacitance here at the input. Now, this for a single stage amplifier like this, this capacitors create a problem, because we might have seen that in our original transistor amplifier that we were using in the conventional circuit that we have. If we take this transistor amplifier circuit, this single stage amplifier, and we used to get a gain bandwidth relation like this, that is gain versus frequency if we plot, that we used to get for example, the curve like this. So, this is actually the low frequency region problem is coming because of this capacitor, and then high frequency gain is reducing because of this Miller, so called Miller effect capacitance. Also, we have capacitance here. So, this low frequency is limited by these two capacitance, low frequency effect, low frequency. This actually creates problem in the high frequency. So, this problem is there in the operation amplifier as well, because after all the operation amplifier, if you see carefully what is involved, they also you have a Miller effect capacitor and then the input capacitors, and the actual operation amplifier in the real world consists of several stages. It is a multi-stage amplifier. So, essentially if you see the operation amplifier simplified circuit, it looks like this, that you have the input stage wherein it is a difference amplifier here, negative voltage, and then this is connected to positive voltage. Then this output actually invariably applied to the one more stage of difference amplifier. Again this is given to the minus supply, and then this output is fed here, and then the other output also fed to the next stage, and then this output is actually given to the output stage, which is similar to what we had discussed in the earlier stage. The output stage consists of some more amplifiers that we will see later, the current limiting and so on. So, if you see this one, this is a minus input and this is a plus input, and you get the output voltage. It is a multi-stage transistor amplifier. So, now what is the issue with the multi-stage transistor amplifier? The multi-stage transistor amplifier has multiple poles and zeros. That is the worry, because for example, if you take this, that you have a capacitance from here to here, and then you also have a capacitance from here to here, and so on, that all the stages have their own Miller capacitances, and then also you have this, and then also you have the input capacitor also there, which limits the low frequency performance. Now, that is, there are multiple Miller effect capacitors, similarly there are multiple input capacitors. Input cap, and the performance of this stage, frequency response performance of this stage is actually related closely to how this is coupled to the next stage and the capacitor associated with this. Similarly, the performance of this stage, frequency response of this stage is actually coupled to the related to the next stage. So, net result is that if we have several capacitors, then if we try to plot the frequency response of this multi-stage amplifier, it looks like this. That is, if you plot frequency versus gain relation, then you have, for example, many 3 different poles, for example, you will get in. So, you have a first pole here, and then the second pole in the second stage, and the third pole in the third stage. So, this is the frequency response of the multi-stage amplifier, similar to what we are discussing the op-amp circuit. Now, what is the issue with this multiple amplifier and then frequency response of this multi-stage amplifier? The problem is that the circuit can oscillate, that is the main issue actually. That is, instead of working as an amplifier by putting the 2 resistance, and now we are shown that it can be used for amplification, but actually instead of working as an amplifier, it can work as an oscillator if the phase shift around the loop and then the gain around the loop are satisfied. So, circuit can oscillate. This is the main issue that we have to worry. Instead of amplifier, it can act as a oscillator. The reason is that when here is a pole, this is created by one RC component, mostly it is actually Miller effect capacitor and the resistance associated with that. So, Miller effect capacitor first stage and the resistance associated with the input can create this pole 1, and then you have the second pole here P 2 and third pole here P 3. So, P 1, P 2, P 3 are poles created by the Miller effect capacitors. P 1, P 2, P 3 are poles created by the Miller effect capacitors. Now, what is the problem? With each pole we know the period is produce a 45-degree phase shift, because each one acts as a RC, each pole you have a RC filter effect. So, each pole produces a 45-degree, each pole produces a 45-degree phase shift, 45-degree phase shift at pole frequency. Pole frequency actually is given by 1 by 2 pi r c. Now, and as you increase the frequency, this has a 20 dB slope, 20 dB per decade slope, and then the phase actually the phase shift continuously increases. 10 times the pole frequency, phase shift becomes 90 degree, 10 times the pole frequency, 10 times the pole frequency, the phase shift, this phase shift between input and output, becomes 90 degree, and also the amplitude reduces by a factor of 10, and also the amplitude comes down by a factor of 10. The output amplitude comes down by a factor of 10. So, when we have multiple poles like this, so each pole produces 45-degree phase shift here, and then 10 times the pole frequency it becomes 90 degree. The next pole comes, again it produces a 45-degree phase shift. So, it is possible at this point you can have 135-degree phase shift. Then it at this point it can become 180 plus another 45 that it creates, because this phase shift slowly increases, becomes 180, and then it becomes another 45-degree phase shift. So, if you see that one, then another 10 times pole frequency it can become 270 degree. So, when you have a multiple pole frequency, that it is we can have a phase shift of more than 180 degree, and if the phase shift goes more than 180 degree, and if in feedback we are already giving a 180 degree phase shift, the net result is the amplifier can oscillate at some frequency because of this multiple poles. This is one of the major problem in using the amplifier. So, if we have to use the amplifier for practical use, then one have to worry about this oscillation, and we have to make our effort to stop these oscillations. So, normally the manufacturers do the frequency compensation inside the operation amplifier itself, so that the amplifier is stable and then it works as an amplifier. So, that is done invariably in the first stage by adding RC at this point. So, we have plus here, and then the minus input and the plus supply, plus 15 volt supply here, and the input stage if you see that you add this RC. So, RC is added such that you can shape the open loop frequency response, because open loop frequency response which is like this, that we had shown the gain versus frequency curve, there are multiple poles. Now, by one can actually do this and bring down the frequency response is a like this, as if it is a single pole frequency response, and the pole frequency is now shifted to this. This is actually given by 1 by 2 pi r c, and then one can bring down to a very low frequency, and then now this is uncompensated amplifier. That is, without this RC network, the uncompensated op amp, this is compensation. With compensation, you can bring it down like this. With this, the idea is that we have here at this point 45 degree phase shift, and then the phase shift increases, and then it can become maximum only 90 degree, because for RC network the phase shift cannot go more than 90 degree. So it acts as if it is a single pole amplifier. So by adding RC network, the frequency response looks as if frequency response looks as if it is a single pole amplifier. It is a single pole amplifier. Now that is at pole frequency. Now you can have at pole frequency, see the total phase shift will be 45 degree, and maximum of only 90 degree phase shift is possible. Phase shift is possible. So the amplifier, so there is no possibility for oscillation. There is no possibility for oscillation. In fact, this is what it is done in most of the operational amplifier. This they call it a dominant pole compensation. This is called as dominant pole compensation. Now, the dominant pole compensation is good, it works always, there is no problem at all, but only drawback of this scheme is that the open loop gain is drastically reduced. We achieved this stability by drastically reducing the overall open loop gain of the amplifier. So, the dominant pole compensation is good. So, if we look at the positive part of it is that it is very stable. So, you can depend on this, it will never oscillate, but the bad part of it is the open loop gain is drastically reduced. Open loop gain is reduced drastically. So, the frequency, the open loop gain is drastically reduced, except at low frequency. All if you look at the high frequency, the gain is drastically reduced. This is the bad part of it. Nevertheless, most of the op amp, particularly the general purpose op amp, follow this route, that is they do the dominant pole compensation, so that we can use the op amp for variety of applications. So, if I take the operational amplifier and then look at the closed loop gain, then if I put the two resistance, for example, here to give the signal here, and then this is RF and R1, So, that gain is actually given by 1 plus Rf by R1. Now, this is the gain at low frequency. Now, what effect the gain has got because of this finite closed loop gain, because original amplifier that original operation amplifier that we had looked at had a infinite gain and it had an infinite frequency response. That was the assumption that we made and then derived this relationship. So, the ideal op amp if we take that, it has infinite frequency response, then it had infinite frequency response, then infinite gain. But then both are not valid for the practical op amp. For practical op amp, frequency response is limited. And second one, gain also limited. Now, considering these two limitation, now what is the closed loop gain that you get? Is it true that gain is all the time 1 plus Rf by R1? Actually, it is not true, that practically this is not true. So, what is the new frequency response curve that you get considering this limitation? So, the actual frequency response will be like this. If you look at the actual frequency response, it looks like this, that you have, for example, that you have open loop gain after compensation, it comes like this, a single pole response, frequency versus gain. Then if I set the gain, this is a closed loop gain, for example, if I want gain 10, so I put this may be actually 20,000, for example, for 741 the DC gain would be around 20,000 minimum, and then this is falling at the rate of 20 dB per decade, and the closed loop gain 10 at low frequency. At low frequency, the gain is closed loop gain also 10. As you increase, then it as increase the frequency, at one point of time it meets the open loop gain frequency response. This is the open loop gain, and this is a closed loop gain. It meets at one point, and thereon it follows the closed loop gain. So, the amplifiers, new amplifiers bandwidth is like this, that is the gain versus frequency. If you plot that, you get, that is the amplifiers bandwidth, that is a DC, this is a gain 10. Suppose for 741 we have a gain bandwidth product of 1 megahertz, for example, for 741, for example for 741, gain into bandwidth is equal to 1 megahertz. That means, and the gain is unity, the frequency is 1 megahertz. For example, at unity gain is 1 megahertz. So, when the gain becomes 10, this actually become 100 kilohertz. So, if I have that means that is gain is equal to 1, closed loop, open loop gain, that is open loop gain is equal to 1 at 1 megahertz. Open loop gain is equal to 10 at 100 kilohertz. That means, if I have an amplifier of gain 10, that is closed loop gain 10, then its bandwidth will be 100 kilohertz. That is, if closed loop gain is 10, closed loop gain is 10, gain is 10, then bandwidth of this amplifier, this gain 10 amplifier is equal to 100 kilohertz. So, the gain bandwidth, the new amplifiers gain is actually limited by this frequency response. That is, at 100 kilohertz you will find it is the gain is not 10, actually it will be only 7, because the pole frequency of this amplifier, new amplifier of gain 10 is 100 kilohertz. That is, the pole frequency of the gain 10 amplifier is 100 kilohertz. So, at 100 kilohertz this amplifier will have 45-degree phase shift. So, at 100 kilohertz this amplifier will have amplifier of gain 10 at 100 kilohertz this amplifier of gain 10 will have phase shift of 45 degree. That is, if you look at the amplifier and then say gain 10, and if it is a 741 of gain bandwidth product 1 megahertz, then this is the input and then the output is here. The phase shift between this and this will be 45 degree. So, if you look at this and this, the phase shift is 45 degree here between input and output, because at 100 kilohertz. So, basically the phase shift is given by theta is given by tan inverse of f by fp. So, fp is the pole frequency. So, once pole frequency is known and then the applied frequency is known, one can find what is the theta that one can get the at any given operating frequency. So, this problem to be understood, so that one can use the amplifier properly in the actual application. Now, let us see one of the application AC amplifier application, and see what are the issues that one normally faces, and then we come back to this again, discuss about other issues like slew rate and so on. So, we will see one of the application at this point of time. So, we apply this amplifier or we design amplifier now for the so called lock-in amplifier. So, let us take design of a lock-in amplifier. Now, the lock-in amplifier originally was used only to extract the signal which is buried in the noise, and also lock-in amplifier concept is used to separate out in phase and out of phase components. So, basically lock-in amplifier is used to extract signal which is buried in noise. noise. Typical example would be that if the noise is 1000 times more than the signal, and even you can extract the signal without much difficulty. For that purpose only the lock-in amplifier is used. Then the second is separate out the in phase and out of phase component. Separate out the in phase and out of phase. Out of phase component. Like for example, if I have a resistance and capacitor, the capacitor gives you in phase component, capacitor gives you 90 degree out of phase component, resistance gives you in phase component. So if I want to find out in phase resistance part of the signal and the capacity part of the signal, one can use the lock-in amplifier and separate out this. Example, say that is, if I have a resistance and capacitor together, this gives you in phase component, this is 90 degree out of phase component, out of phase. To this for example, the signal which is buried in noise is like this, that is, if I have a signal and if it is buried in the noise, where the noise can be several times higher than this, it can extract the signal, this signal alone can be extracted, and the noise can be rejected. For this purpose only lock-in amplifier is used. Let us see how to design such a lock-in amplifier and how it is working. So what is the basic principle involved in the lock-in amplifier, that is extracting the signal which is buried in the noise. So what is done is that if I have a signal and noise, basic principle involved, basic working principle. Now what is done is that, let us assume that we have a signal source and then the noise, and then I will have a assume that I have a signal, and then I pass through the switch, then I have a load here. This is a load, and then we have a switch here. Assume this is a signal plus noise. Signal plus noise is there. Now we want to extract only the signal and we want to get away from the noise. Take this example. Now assume that it is a sine wave source. So I will take this input as a sine wave. Input is sine wave with the noise. Output required is only DC voltage, proportional to sine wave. We are not looking for the exact sine wave to be reproduced at the output. We want here the DC voltage proportional to sine wave, but it should not depend on the noise. There is a noise this output voltage will not have any component due to the noise. That is what we are looking for. Now how will you achieve this? Now one can do this in the following manner. Assume that we have a sine wave, that is, we have a input sine wave like this. Then we will have a switch here. Then I operate the switch. Switch is on, that is, this is positive off cycle. You have a positive off cycle, and this is a negative off cycle. So, this is a positive and this is a negative off cycle. Okay. Keep the switch on, that is keep the switch on, switch S1 on during positive half cycle, and keep the switch F2 on, keep the switch S2 off during negative half cycle. Then at the load you will get only positive half cycles. So, the load at the load point, if you see, you will get a signal positive and the negative is not appearing, you will get this. This is the load voltage. Assume this is ideal switch, then I will switch on only when the signal is positive, I will switch it on, and when the signal is negative, that is when the signal is positive, I switch it on, when the signal is negative, I switch it off. So, then I will get here only the positive half cycles at this point. So, you will get only the positive half cycles at this point. Now, what is the what is that we are trying to achieve by this? Assume that we have signal which consists of signal plus noise, then I will draw that I will have a signal which actually has a noise continuously. Now, when the switch is on, then if I look at the load side, I will get during this time whatever was there, it is not a diode, it is a switch. It allows both positive and negative during the on time. So, switch is a bilateral switch. Switch S1 allows both positive and negative voltage as it is. That means, at the across the load I will get the signal which is I switched on with respect to signal, I am switching the switch with respect to the signal. So, you will get at the output positive off cycles, of course with the noise may go positive and as well as negative. So, if I look at the signal now, that is time versus voltage, if I plot, I will have this and there no voltage comes here, no voltage comes here. Then during this time whatever signal noise is there, that also will come along with the signal. So, you will get, so both signal and noise coming here, both signal plus noise is the output, this is the output voltage. Both signal as well as noise are appearing at the output. Now, but negative is not coming, but signal is always positive. You see this, signal is always positive. Here signal is always positive, signal is always but the second point is noise is positive sometime and negative sometime. So, if I average the signal at the output, then I will get the signal is continuously added because signal is positive. So, what can be done is that I will have a signal and the switch is like this and then I have this, then I will keep the capacitor here such that I can also do the filtering in the following manner, that is because I want to store the average the signal plus noise. So, I can do in the following manner, instead of having the load like this, I can have a switch, then I can put on RC like this. Now, at this point you will have signal plus noise, signal plus noise that is coming here. But at this point if I see that is a V 0, then this is a capacitor used to average out. At this point I will have a DC voltage, DC voltage, DC voltage which represents only signal. What happened to the noise? Actually noise got averaged by itself, because noise is positive sometime and negative sometime. So, the by RC filter action, this RC filtering action, this RC filter action actually removed the noise, by averaging. Of course, the time constant of RC should be much larger than the frequency components of the noise, then only averaging is possible. So, we assume that our RC component is very large, the noise by averaging. This is if RC time constant is larger than frequency components of the signal. So, one can the noise get averaged out, and the it gives you DC voltage proportional to the signal alone. Proportional to the signal alone. So, by averaging technique, one can remove the noise. So, basically lock-in amplifier works by averaging, that by averaging the noise is removed. So, basically by averaging noise is removed. So, this is the basic working principle of the lock-in amplifier. So, this noise rejection happens only if the switching is done correctly, because this should be on during the positive half cycle and it should be off during the negative half cycle. Then the averaging can then only averaging can take place. So, one should find out what is the true zero crossing points for the signal. So, so for lock-in action to take place, then one have to find the true zero crossing points of the signal. So, for lock-in action to take place, for lock-in amplifier to work properly, the switching must be done. At true zero crossing point of the signal. Then only the lock-in amplifier can be useful. Now, of course, we set here only one off cycle switching, that is positive half cycle alone we are switching and negative half cycle we are not switching. We can also do it in both cycles, plus and minus, and reverse the signal and put it in both sides, so that still averaging can be done for both positive and negative. So, we can do that in the following manner. We can say that how to do the both side switching. So, both side switching example I can show you now. What can be done is, for example, if the signal is coming out from the operation amplifier, for example, I have a signal, that is a AC signal coming out from here, then I can do the switching in the following manner. For example, I can have switch S1 and then here S2, I have S1, S2, then this I can take here, then put S3, then also I can put one more switch S4. This assume that I give it to the operational amplifier. So, I give it to a difference amplifier. For example, I give this, then sorry, so minus, keep this, then here I put this, this take it as output. I have R and R. So, for example, if it is a positive half cycle, then for example, if it is a positive, during positive half cycle, I switch on S3 and then S4 is off. So, I will do like this, that is during positive half cycle, during positive half cycle, I will switch S3 on, S4 off, then S2 S1 off, S2 on. That is during positive half cycle, what I do is I will switch on this and switch off this. So, that signal can come here and half of the signal will appear here. So, you will get whatever voltage there, half the voltage will be appearing at this point. So, V by 2 you will get, and then this switch is open at the time and this is on. That means, now it is acting as a non-inverting amplifier. So, if you have V here at this point, V by 2 you will get, and then that is multiplied by 2, because if I make this also equal to R, this resistance also equal to R, then whatever voltage V here, and that becomes V by 2 and multiplied by 2, that gives you V here. So, this makes, that means this action makes it is a non-inverting amplifier, inverting amplifier of gain 1, that means the whatever input voltage is there, that will appear as it is at the output. So, if this has a noise plus signal plus noise, during that time whatever was there, the same thing will appear at the output. So, non-inverting amplifier of gain 1, that is output will be same as input. The signal plus noise will appear as it is, that is signal plus noise will appear as it is. Now, during the negative half cycle, so during the negative half cycle we discuss negative half cycle. Negative half cycle of the signal. What you do is we will reverse the action, that is I will keep S3 off, S4 on, S1 on, S2 off. That is what you do is with the negative half cycle, I will keep this open and this is closed, so that the plus input is grounded. Now, S3 is open, so no signal is coming here, and then now S1 is on. So, whatever signal is negative signal is there, it will come here, and S2 is open. So, that signal will be applied here, and this is acting as a inverting amplifier. So, this action gives it becomes a inverting amplifier. It becomes an inverting amplifier. So now output will be output will be 180 degree phase shifted. That is minus, the signal will become plus, that is signal become, that is signal again becomes positive at the output, So net result is that if I look at the output V naught, if I look at the output V naught here, so you will have, if the switches are switched correctly, that is during positive off cycle of the signal, that is if I have a signal here, which is positive and negative. During the positive off cycle, assume that you have a signal, during positive off cycle you will get the positive signal as it is. During the negative off cycle, of this, then since the signal is going now through this route and get inverted and come, so the minus signal get inverted, will become a plus again. So again you will get the signal like this. So if we plot the, if we look at the output voltage V naught, that looks like this. So the output voltage V naught, that is output voltage. So time versus voltage, if I plot that, it looks like this. Because whatever noise is there, that will be there plus and minus, that will be going both plus and minus. So you get this is signal and that is the noise that is coming here. So now we got, it is not a rectifier, in rectifier you will never get this minus voltage. In minus voltage, if you put a diode, then I will get signal positive, a noise of positive alone will come, noise of negative will not come. If noise of negative is not coming, then there is no question of any signal averaging. So it is a switch which allows both positive and negative, but we are switching on at appropriate time with respect to signal. So taking signal as a reference, we are switching, that is the crux of lock-in amplifier working. So if I now filter this, that is whatever the noise voltage that we have got at the output, now if I pass through the RC filter, so this is the output of the amplifier that we have got here. So we have these switches and then this is a difference amplifier. So we had these switches here and then we have, so this is the input signal. So now we will have this averaging RC, the time constant of RC is much larger than the noise frequency, then you will get here DC voltage, DC voltage proportional to the signal. Noise is actually getting averaged by themselves. Noise is getting averaged out. Noise is getting averaged out. This is a wonderful technique to reject the noise and extract the signal. This was extensively used in electronics wherever we are processing the signal. So the lock-in amplifier technique, by averaging means we can extract the signal which is buried in the noise. Now, in the beginning we said that lock-in amplifier is used for two purpose. One is for extracting the signal which is buried in the noise, other one is to separate out in phase and out of phase component. So, how in phase and out of phase component is separate out? How in phase and out of phase component is separate out? Components. Because this is also required at many places. For example, if you take an induction motor, the in phase component is actually produce the magnetic field, and then in phase component produce the load current. Load current is actually in phase, and the magnetic field, the torque producing component, is out of phase, 90-degree out of phase component. Similarly, inductor and capacitor, if I take the capacitor current is 90-degree out of phase component with respect to resistance or with respect to applied voltage. Similarly, if I take an inductor, that inductor current is 90-degree phase shifted with respect to the applied voltage. So, many times we want to separate out resistance with the capacitor or resistance with the inductor or capacitor and inductor to be separated out. In that case, it is essential that we separate out in phase and out of phase component. This also can be done using a lock-in amplifier. Only thing is we need to switch them correctly. This switches S1, S2, S3, S4 are to be switched correctly, such that they can be these components can be separated out. Because once you separate out in phase and out of phase components, they can be used for many purposes. For example, if I want to control the induction motor, if I want to vary the, for example, speed, I had to find out the in phase component, then I can control what is the flux level, I can control the out of phase component, so that I can control the flux level in the motor. Similarly, if I know the in phase component, I know the load level of the motor. So, that way they call this the vector control of the induction motor. Like that, very many applications are there. This we see in the next class, how to separate out these components and how to design a lock-in amplifier in detail. So, we will see in the next class how to design the lock-in amplifier. I stop today with this. Thank you.